This lecture looks at some more complicated AC circuits. First, we'll look at an RC AC circuit. That is a circuit which has a driving voltage that's sinusoidal, where there is a resistor and a capacitor in series. The resistance and capacitive reactance in series don't add directly because of the 90 degree phase difference between the currents. Instead, they add like perpendicular vectors. Or in other words, we have a vector of something like xc and a vector r, and there is a resultant vector that has a length of the square root of r squared plus xc squared. So that I0, the current amplitude, is equal to V0 divided by the square root of r squared plus xc squared. Or if we put in the definition of xc, we have V0 divided by the square root of r squared plus 1 over omega c squared. Looking at the amplitude of the voltage drop across the resistor, V of r is equal to I0 times r, which is then just r divided by the square root of r squared plus xc squared times V0. And that's equal to r divided by the square root of r squared plus 1 over omega c squared times V0. And if we divide through by r, we just have 1 divided by 1 plus the square root of 1 plus 1 over omega rc squared times V0. If omega is much larger than 1 over rc, so 1 over the time constant, the rc time constant, then V of r is approximately equal to V0. So there is the value of the amplitude of the voltage is going to be similar to the drive voltage. If omega is much smaller than 1 over rc, then the amplitude of the voltage across the resistor is about 0. So that for high frequencies, the voltage is unchanged or unattenuated, whereas for low frequencies, they are attenuated. So the high frequencies appear across the resistor, and the low frequencies appear across the capacitor. Now let's look at a quantity known as impedance. To do this, we're going to look at the circuit which has a resistor, a capacitor, and an inductor in series driven by a voltage source. The resistance, capacitive reactance, and the inductive reactance in series add like vectors. They do not add directly. You note that xc and xl point in opposite directions and are perpendicular to r, or in our picture we have an xl pointing up, an xc pointing down, and an r pointing to the right. So that we have a resulting vector which has a length that is equal to the square root of r squared plus xl minus xc quantity squared. The magnitude of that vector is known as the impedance, Z. So that we can write in general for a circuit that we have an I0 current amplitude that is equal to some V0 of the driving voltage divided by the impedance of the circuit Z. Similarly, we have that the phase is equal to the tangent of XL minus XC divided by the resistance. If we look at this RLC circuit and specifically and ask how it behaves, what is the current response, then we have this I0 is equal to V0 divided by Z, and V0 is divided by the square root of R squared plus XL minus XC quantity squared. And then we plug in the values of XL and XC, so we have V0 divided by the square root of R squared plus omega L minus 1 over omega C quantity squared. If we look at that carefully, we see that I0 has a peak when omega L minus 1 over omega C is equal to 0. Because at that point, V0 is then, the I0 is just V0 over R. Any place else, any other frequency, the denominator is larger. So the peak is at what is known as the resonance frequency, where omega is equal to 1 over the square root of LC. So we just solved that equation for omega. If we look at a specific example where L is equal to 10 microhenries and the capacitance is equal to 1 nanofarad, and do a plot for two different resistances, the blue curve is for a resistance of 10 ohms. We see a peak structure when omega is equal to the resonance frequency. If we increase the resistance to 30 ohms, this peak drops down. So we see that the resistance, increasing the resistance reduces the sharpness of the peak.